Yesterday, we had a look at the design of reinforced soil walls. So today, let's have a look at reinforced soil slopes. Again, we will start with a look at slope stability issues, then go to the design of reinforced soil slopes. So again, whenever we have like an embankment or a slope, basically we have to look at the various options like what is the height, how much space is available. Then again, whether it is a fill slope or a cut slope like that. If it is a cut slope, of course, like we have no scope for geosynthetics, we go for soil nailing only. But if it is a fill slope, we have various options. So here also again to recap from yesterday, first thing is to determine what is a safe slope angle. Like if space is available, it is the best option. Usually that is going to be the cheapest option. But if land is not available or if land is too costly, or today there is one more constraint, even the fill material may not be available like in many places, or it may be too costly. So then we have to go for a earth retain solution. So again, we can go for a retaining wall or a steep slope. So the first question is like, what is the safe slope angle? Like, now this may look trivial, like, okay, let us determine the C5, do a slope stability analysis. What's the big deal, we might ask. But then it is not as simple because like soil is not a material like concrete or steel whose properties are well defined. So determining the shear strength parameters of soil is not an easy task. So like if we ask a field engineer, like what is a safe slope angle, he would say, okay, it's the angle of repose, like a very common term. So what is the angle of repose? Like, see, normally it is applicable for sands, like dry sands, like just simple method is you take a funnel, pour the sand through that funnel, it takes a natural angle, you can measure that is the angle of repose. So like if you do a direct shear test, like for example, like dense sand, it has a peak and what we call the constant volume or ultimate like that. So basically, like we have this, so we have actually two envelopes, one the peak and another the constant volume. So the angle of repose is equal to the phi CV, we call it, the constant volume friction angle. Like we can measure both ways, like do a direct shear test, from that determine this phi CV, then simply like pour it, measure the angle, determine the angle of repose, more or less it will be equal, like for a dry sand. So, but if soil is dense, probably like angle of repose is for a loose sand. Like, so if the soil is more dense, maybe it can take a slightly steeper angle. And again, angle of repose is at a factor safety of 1. Like, but in actual a slope, we want a factor safety also. So it has to be somewhat flatter than the angle of repose. See now, if you come to a cohesive soil, like our experience tells us, like it can stand at a steeper slope, like a material like rock. It's a very strong cohesive material. It can stand 90 degrees, no problem like that. But soils like clay, like we have done that experiment, like we do like a compaction test or prepare a sample for unconfined compression test, like a clay or silt. You compact it in a mold, you remove the mold, it's standing perfectly vertical like that. But then the question is how long? Like when you put that sample into water, put it in a bucket of water, what happens? The sample which was apparently strong, it becomes mud like that. So this cohesion, the so-called cohesion, is a tricky thing. So normally we learn like sands and gravels, we call it cohesionless soils, and clays, silts are cohesive soils. Sometimes again this terminology like C5 soils like that. So this cohesion of clays or silts, like it's function of like the water content, like when the clay is very much wet, it's almost like a mud or liquid, but you put into the air, you dry it, it becomes stronger and stronger like that. But again, you put that dry lump into water, again it becomes mud. So that's why we call it apparent cohesion. It's only apparent, it is not permanent. So one simple example is like a unconfined compression test. Like imagine like there is a ground. First of all, if it is sand, it is very difficult to get a sample, like undisturbed sample. But assuming we take it, the moment you take it out of the tube, it's going to collapse. Like we know, it cannot stand unconfined. But a clay, assuming it's a normally consolidated clay at a depth of 5 meter, then we know what are the stresses. Like I've done this simple just to give a feeling of the numbers. So vertical stress is 80 kPa, and assume water table at ground level, then the effective vertical stress is 30. Similarly, the horizontal stress we can calculate once we know K naught. Let's assume this value. So this also we can calculate like that. Pore pressure we know, like it's 5 into 10 is 50 kPa. So now let's assume we take a borehole, you take that sample, like a tube sample, then you eject it from the sampling tube. So we get the sample. Now what are the stresses? Total stress is 0. Vertical stress, horizontal stress is 0. Because the weight of sample we can negligible. What about effective stress? Like we don't know. Like we don't know what is the pore pressure. Like that. Then suppose I draw a Mohr circle for this sample which is unconfined. It will be like we know the stresses are 0, both vertical, horizontal, like it's a point. See now I load it actually, do the unconfined compression test. The Mohr circle becomes this, the vertical stress maximum is the unconfined compressive strength. I can draw the Mohr circle. The failure envelope becomes horizontal. We get what is the cohesion, which we call the undrained cohesion. And we call the undrained friction angle is 0. Like that. See now, suppose like if you had an instrument which could have measured the pore pressure inside, then we could have drawn the effective stress circle. And here, like when, like here, the stresses are here. Like when you remove the sample from the ground, what are the stresses? It is 0. So what does the specimen tries to do? It tries to swell like that. But can it swell? Because soil is saturated, all the pores are filled with water. So if it wants to swell, either water has to expand or vacuum has to be created in the voids. So that is not possible. It can swell only if the water can flow into the voids, but since it is in the air, there is no access to water. So that is why the pore pressure goes into below atmospheric, or we call it pore pressure in tension or negative pore pressure like that. So that is what gives it strength. Although it is unconfined, like we don't see any confinement, but inside effective stress is there because the pore pressure is negative. So otherwise, there was no strength. And suppose if I put the sample into a bucket of water, so then the specimen can swell because it has got access to water, it absorbs water, then the pore pressure which was negative, it becomes positive, or it becomes practically 0 because it's atmospheric pressure. So then there is no confinement. I can find the specimen collapses. So in the case of the clays or silts, the so-called cohesion is because of this negative pore pressure. So whenever it becomes saturated, its strength becomes 0. So again, to recapitulate or summarize, like in the case of fine-grained soils, they can develop significant cohesion. Whereas sands, it can develop, like if its sand is slightly moist, it has some very slight apparent cohesion, but not much. Whereas clays or silts, the more fine-grained, the suction can be more like that. So this has an important effect on stability. Like if I make an embankment of clay or silt, then I can make a cut vertically. And it may remain stable for quite some time like that. Why? Because again, the compacted soils are unsaturated. The pore pressure is negative. So it gives shear strength to that. But if that embankment is exposed, it rains over a period of time, many years, the soil becomes saturated. Then you find one sudden day, it has collapsed like that. So, like basically we have to get what is short term and long term. Like short term, it remains even a steep slope, 45 degrees, 60 degrees, even 90 degrees, it may remain stable, but then not for very long. Over a period of time, it will collapse. Then again, what you have to remember is, like, most soils are cohesionless. Only like cemented soils, they have some cohesion. Similarly, heavily over-consolidated soils, like throughout in their geologic history, if they have been heavily over-consolidated, it may have some effective cohesion. Similarly, residual soils, soils which are formed in situ, they also have some cohesion. Otherwise, most sands, gravels, clays, silts, they are purely cohesionless. Strength is purely friction. So they have strength only if confining stress is there. Now, when you do a stability analysis, sometimes we look at long term, short term. Like if I am making a building, the foundation, which is more critical, when is the factor of safety lowest? That means what we call the end of construction. As soon as I construct the building, the full load I have applied, the soil stresses have increased, but then the soil has to consolidate. Then with time, the excess power pressure dissipates, the effective stress increases, factor of safety increases, like that. Similarly, if I construct an embankment on a soft saturated clay, so this applies stresses increase, so the clay, so initially all the increase in stress is carried by the pore water pressure increases, then with the time it dissipates. Then the confining stress increases, effective stress increases. So effective strength increase means shear strength also will increase. So with the time, shear strength will increase. That means stability will increase. So most critical is at the end of construction. But what about this embankment? So it is made of compacted soil. Let us say it's a silt or a. So it is unsaturated like that. So it has suction or negative pore pressure. So initially it is strong. Then with the time, it experiences 2-3 years monsoon, few years monsoon, it may get saturated. So when it gets saturated, what happens? The pore pressure, that the suction goes, it may become positive. So shear strength loses. Or what we call the effective stress reduced with time. So initially the pore pressure was negative, so effective stress is more. When the pore pressure becomes zero, it reduces. Pore pressure could become positive also, so effective stress reduces. That means shear strength reduces the time. So what happens to the factor safety? It reduces. So for that embankment, actually long term is critical, whereas for this part, short term is critical, like that. So when we do a stability analysis, we have to do the appropriate analysis, and we have actually effective stress analysis, in which we use the effective stresses and the effective stress shear strength parameters C dash, phi dash. So this can be determined from either a consolidated undrained test with pore pressure measurement or a CD, consolidated drain test. Both is possible. So this we call an effective stress analysis. So wherever long term is critical, always we should go for a effective stress analysis, because that is give the real picture. Suppose we go for a total stress, actually it gives a much higher factor of safety. And wherever short term is critical, we can do any approach. We can do the total stress approach, because short term is critical. So that we are taking care with the total stress approach. And anyway, we know with the time factor of safety will increase. Or we can do effective stress. Both are equally applicable. Because sometimes, see, if you want to do the effective stress, we should know the pore pressure. Whereas total stress is easier. So that is why it's more convenient like that. So, but if I do a total stress analysis, then initially I'll get a higher factor of safety, but after a period of time, that is going to reduce. So practically in projects, this can create a problem. See, sometimes what happens, the contractor, he constructs. Sometimes there is a maintenance period, so like 1 year or 5 years. So during that period, nothing happens. Maybe the failure occurs after 8 years or 10 years. Then who has to manage that? Then the PWD or NHAI, they have to manage with that actually, like that. So we have to take a long-term approach, then only we have to. Because normally the main problem is today we have is like we have land is very costly. Acquiring land is very difficult. Not only the cost, because a lot of protest strikes, we know how it is. Then second problem is like getting the fill material. That is also a problem. Like many places, see where I come from Kerala, it is very, very difficult actually. Like we have 2 3 years back, once the sand was imported from Cambodia. Can you imagine? Actually, not for earthwork, for building construction. Then actually it was the customs clearance, some issue was there actually. Then later on, Gujarat sand goes to Kerala like that by ship, like that. So this is things are changing like that. So not only in Kerala, many places now soil is very very expensive. And I was told by Professor G.V. Rao that some I don't know some convention after many years like we cannot use these materials anymore like that, like soils in construction like that. Some law is going to come. So the any project, the pressure is always there to go for steeper slopes. Now, I was working in a railway project, like we have this dedicated freight corridor, so dedicated line for freight trains actually. So I was working in one project in the eastern corridor. It's about 350 kilometers long stretch. And can you imagine what is the cost of earthwork? Make a guess. It was about 1,000 crores, like 1,000 crores actually, purely earthwork like that. So then you can imagine like, and our like RDSO had a specification like the embankments, it cannot be steeper than 2 horizontal, 1 vertical, which is safe like that. So normally if you have this criteria, your cost goes up, it becomes 1,000 crore. So World Bank, they are the funding agencies, like they want to reduce, like optimize. See, normally like World Bank, they're against this type of what they call the prescriptive approach. Like this is a prescription, like, okay, what is a safe slope? 2:1. Like then he says, like, why do you want to be so restrictive? Let give the freedom to the contractor who does the EPC contract, that means design and construct. Let him do the testing, do the analysis, let him find a slope stability analysis. See, in principle, it's rational, but when you do actual practice, it's very tricky because we know the kind of soil testing we have here. Like we can come with any C5, like whether it is undrained, drained, direct shear, triaxial, nobody knows actually. C5 comes to me as a designer, I will do the slope stability analysis, 60 degrees may be safe like that. But if we construct, is that acceptable like that? So finally, fortunately, the railway also very, very strong like that. Nothing doing, we will go with 2 horizontal, 1 vertical like that. But then if you want, there is a solution actually. Like it's not that we cannot make it steeper. With today, fortunately, we have a very good technology, the soil reinforcement. We can make it 45 degrees, 60 degrees, 68 degrees, no problem. But then we have to put the, like, not make it 45 degrees without reinforcement. People are doing that actually. Like, actually, we have in India, we have a lot of, so much quantity of reinforced soil walls, but very less slopes. Because people are like earlier, we were making 1:1 slopes in the DPR, very common like that. Then you find on the slopes, we have to put a pitching actually to erosion control. On a 45-degree normal, pitching or riprap doesn't stay. Then they go for what is known as grouted riprap. That means put stone, put some mortar like that. Then after a fine time, like within 1 year, that mortar has cracked actually. That means there are some movements like that. So a lot of things. Once I went to a site, there the same site actually, they were having some slope problems actually. Then I looked, it becomes steep. Then I asked, looks very steep. How much it is? 45 degrees? Then that person said, I think it's around 60 degrees like that. So we are constructing very steep slopes without reinforcement, which is actually not correct actually. Provided we use the correct design, then we can have a very good. So I just spent some time like just to this safe slope, actually the fundamental step, but there itself we make the lot of issues actually. We have to be very, very careful. Then another simple thing is like we suppose we do a direct shear test. So we do it at 3 or 4 values of normal stress. Normally what we do, we draw a straight line, best fit line, and we call this cohesion, and we call this friction angle actually. So we give a physical meaning actually. Like, suppose what is the equation of a straight line? Yeah, y is equal to mx plus c. Like, if we call that, if we just call this what is called c and m, no problem. Like, we are very clear. The problem comes when we go with a physical interpretation like c or phi, like that. So only like it means basically this envelope is curved. That's all, like that. Because even friction we have studied, shear strength comes from like mineral to mineral friction, dilatancy, then there is something known as particle rearrangement, then even actually it's not angle of friction. A better term would be angle of shearing resistance, like because it's not only friction like that. So, like when I draw this envelope, see within this range, if I look, this is okay because my calculated strength is along this line, which is less than the actual. So I am safe. But if I go this side, the strength predicted by the straight line is more than my actual, like that. See, actually, we don't know what is in this range actually, but we assume it is like this, like that. So if I use this straight line equation, I over predict. And many slope failures are very shallow. Like normally we have drained failures, undrained failures. Like if it is a clay, normally it is undrained, it's fairly deep. But how does a sand slope fail actually? Like I don't know if you have studied about infinite slopes. Like I have this here. If the slope was infinite, this is the way it should fail. And mainly the factor of safety is tan phi by tan beta if it is dry, like that. So if I look at a shallow failure, it is almost like an infinite slope failure. It can fail that way. So what is the stresses here, vertical stresses? It's very, very low. And what is my shear strength in this? If I take the straight line equation, I over predict my strength, so it give me a higher factor of safety, like that. So this is another part actually in the this C5 business, like that. So mainly like slope stability, we have to choose the parameters correctly, whether drained, undrained, short term, long term, that is one question. Then even doing a straight line business, that can also get into problems. So this slope stability analysis, see in principle it can be done actually, provided we get the correct parameters, we use the appropriate method, nothing wrong with that. But actually implementing, especially in our kind of setup, like whether geotechnical engineering is not that much advanced, testing facilities are not that good, it could be problematic. So normally courts give a prescriptive approach. So they something like what you call the cutting the Gordian knot, like uh, like if you want to like if you have a knot, like if you want to untie, it's very tricky. Best thing is you take a knife and chop it off. So that's what the standards have done. Okay, adopt two horizontal, one vertical, which is works for most type of soils. It's not that always, like if you have a very plastic clay, even 2:1 may not be safe enough like that. But normal kind of soils, this works. Same thing with railway also. Like so that part is answered. Like if you are doing a highway or railway embankment, what is the safe slope? Most cases, two horizontal, one vertical. So anything steeper, I have to go for either. And again, this is the IRC code. And here also, if you read, it's very interesting. Like side slope shall not be steeper than two horizontal, one vertical, unless soil is retained by suitable soil retaining structures. So what do you make out of that? Like one person told me, like suppose I have a retaining wall, soil is retained, then I can have steeper. Actually, I would not blame him. Actually, this sentence, actually, it is not. Even our code is not. It creates more confusion. Like actually, So again, we have these options. Like one, we go for like like if there is no extra space available, then I have to go for a full height vertical wall. No other option. But if some space, this is conventional retaining wall with this one. Normally, what we call toe wall, like masonry wall, give-in wall, like that. Or we can go for a reinforced soil retaining wall with a back slope, like again. Then another option is go for a reinforced soil slope, like that. So we have these three options. So each project we have to evaluate which system is the best in terms of cost, performance, construction time, availability of materials, then select the appropriate option. See now, let's go to the reinforced soil slopes, which is today's topic. So now again, it's similar to a wall. The only difference is, okay, the inclination is more, plus the emphasis on facing, the importance of facing is somewhat less compared to the wall. Then what are its uses? Like one is to make the side slopes steeper to save land. Then again, to reduce the volume of fill, like steeper means the volume of soil can be reduced. So earlier it was not a big problem, but now it is also a serious issue. Then use poor quality of soil. Like as I mentioned, like 2 horizontal, 1 vertical, for a reasonably good fill, it's okay. But if I don't have that kind of fill, I may have to go even flatter. So I can use, if suppose I have a poor quality soil with reinforcement, I can make it steeper. Then to increase stability, like suppose you want to make it more safe, especially earthquake, or if it is a very like a large height slope, or it is supporting some structure, again we can go for reinforcement. Then another is to get better compaction near the slope face. Like how do we do the compaction? Like compaction test. Like we put the soil into a mold, a rigid mold, then compact. But suppose I just put the soil here and try to compact, will it get compacted? Like, because soil has to be confined actually. So when it is on a slope, if I move the roller, the soil moves sideways actually. Like, but inside, when I move from the edge of the slope, this side gives confinement, so it is easier to compact. So always slope, it's difficult near the slope face to get good compaction. Then another is reinstate failed slopes. Like some slope has already failed, then we'll have to put it back. Then with the reinforced soil, it becomes easier.